Everything you learned about slipping on ice in physics class was completely wrong. And it took German scientists 200 years to prove it. Picture this. For 2 entire centuries, the brightest minds in physics have been teaching the same explanation for why we slip and slide on icy surfaces. Teachers, textbooks, and even Nobel Prize winners have confidently stated that pressure from our body weight and friction from our footsteps melt the ice beneath us, creating that treacherous slippery layer. But here's where it gets controversial. They were all mistaken. A groundbreaking research team at Saarland University in Germany, spearheaded by materials simulation expert Dr. Martin Musser, has just shattered this long-standing scientific dogma. Their revolutionary discovery reveals that the real culprit behind ice's slippery nature isn't pressure or friction at all. Instead, it's something far more fascinating and complex: molecular dipoles. The truth is, neither pressure nor friction contributes significantly to creating that thin liquid layer that makes ice so treacherous, Dr. Musser declared, essentially throwing 2 centuries of established physics out the window. But wait, this is the part most people miss. To understand why this discovery is so earth-shattering, we need to dive into what scientists previously believed versus what's actually happening at the molecular level, the old guard theory that ruled physics classrooms. For generations, the scientific community rallied behind a theory proposed by James Thomson. Yes, the brother of the famous British mathematician Lord Kelvin, back in the 1800s. Thomson's explanation seemed logical enough. When you step onto ice, your body weight creates pressure, and the friction from your shoe sole generates heat. Together, these forces supposedly melt the ice surface just enough to create a microscopic water layer that sends you tumbling. This explanation became so entrenched in scientific thinking that it appeared in virtually every physics textbook worldwide. Students memorized it, professors taught it, and researchers built upon it. During harsh winter months, when people slipped on icy sidewalks, everyone confidently pointed to this pressure and friction theory as the explanation. Dr. Musser's team, which includes computational material scientist Dr. Ashraf Attila and postdoctoral physics researcher Dr. Attia Sergei Sukhomlinov, decided to challenge this centuries-old assumption using something Thomson never had access to: advanced computer simulations. The molecular truth that changes everything. Here's where the story takes a fascinating turn. The German researchers discovered that the real action happens at the molecular level, involving something called molecular dipoles. Now, before your eyes glaze over thinking this is too complex, let me break this down in simple terms. A molecular dipole forms when electrons in a molecule aren't shared equally between atoms. Think of it like a tiny magnet with a positive end and a negative end, creating an invisible force field around each molecule. In ice, water molecules arrange themselves in an incredibly organized crystal lattice. Imagine a perfectly structured 3D puzzle where every piece has its designated spot. But here's the game-changing revelation. When your shoe contacts the ice surface, the molecular dipoles in your shoe sole interact with the molecular dipoles in the ice crystals. This interaction doesn't melt the ice through pressure or heat. Instead, it disrupts the perfectly organized crystal structure, creating what physicists call frustration. In 3 dimensions, these dipole-dipole interactions become frustrated, Dr. Musser explained, describing how competing molecular forces prevent the ice from maintaining its stable, organized structure. This frustration instantly transforms the ordered crystal lattice into a chaotic, disordered mess that eventually becomes liquid, and that's what makes you slip. The process happens so quickly and at such a microscopic level that it appears instantaneous to our naked eyes. The absolute zero bombshell that defies logic. And this is where the controversy really heats up, or should I say, cools down. The research team made another discovery that completely obliterates another widespread scientific assumption. For decades, winter sports enthusiasts and scientists alike believed that skiing became impossible at extremely cold temperatures, particularly below -40 degrees Celsius. The reasoning seemed sound. It's simply too cold for any liquid film to form beneath the skis, so there's no lubrication for smooth gliding. That assumption, it turns out, is also completely incorrect. Dr. Muser revealed, dropping yet another scientific bombshell. The dipole interactions continue working their magic even at temperatures approaching absolute zero. That's roughly negative 273 degrees Celsius, the coldest temperature theoretically possible in the universe. At these mind-bogglingly frigid conditions, a liquid film still forms between ice and ski surfaces. Granted, this film becomes thicker than honey and far too viscous for any practical skiing, but it exists nonetheless. This revelation challenges our fundamental understanding of how matter behaves at extreme temperatures and opens up entirely new questions about molecular interactions in conditions previously thought impossible for liquid formation. Why this discovery matters beyond slipping and sliding. The implications of this research extend far beyond explaining why we lose our footing on winter sidewalks. Dr. Muser's findings fundamentally alter how physicists understand phase changes at solid-liquid interfaces, a phenomenon crucial to countless industrial processes, climate science applications, and even space exploration. Consider the broader scientific landscape. If we've been wrong about something as seemingly simple as why ice is slippery, what other long-held assumptions in physics might need serious reconsideration? This discovery, published in the prestigious journal Physical Review Letters, represents more than just a correction to textbooks. It's a reminder that science continually evolves, and even our most confident explanations can be overturned by new evidence. The research methodology itself deserves recognition. By utilizing sophisticated computer simulations that can model molecular behavior with unprecedented precision, the team could observe interactions invisible to previous generations of scientists. This technological advancement allowed them to see what Thomson and his contemporaries could only theorize about. The controversial question that demands discussion. But here's what really gets me thinking, and I'd love to hear your perspective on this. If the scientific community can be so definitively wrong about a phenomenon as common and well-studied as slipping on ice, how many other established facts in physics, chemistry, and other sciences might be equally misguided? Some might argue that this discovery proves the beauty of scientific progress, that we should celebrate the self-correcting nature of scientific inquiry. Others might question whether we should be more skeptical of scientific certainties that haven't been rigorously tested with modern technology. There's also the practical consideration: should textbooks immediately update this information, potentially confusing students who've learned the old explanation? Or should educators gradually transition to the new understanding while acknowledging the historical context of the previous theory? What's your take on this paradigm shift? Do you think it's exciting that science continues evolving, or does it make you question other scientific principles you've taken for granted? Should we be more cautious about accepting scientific explanations as absolute truth? Or does this discovery actually strengthen your confidence in the scientific method's ability to self-correct? The conversation doesn't end here. In fact, Dr. Muser's research opens up entirely new avenues for investigation. As we continue unraveling the mysteries of molecular interactions, who knows what other long-standing assumptions might crumble under the weight of modern scientific scrutiny? Share your thoughts below. Are you team exciting scientific progress, or team healthy scientific skepticism? The comment section awaits your perspective on this controversial revelation that's rewriting physics textbooks worldwide.